We had talked about receiving signals in the presence of noise. Now let us move on to slightly. So till now, what we have talked. Till now, what we have assumed is that say the receive we send a signal SMT or SM and receive R, or rather send SMT and right, and since SMT can be expressed as
So this is lecture number 20, right?
yep. Why?
So I think lecture number 19 and
कर ले
we studied
सिर्फ
about
19 लोग हैं
Sorry.
say lecture number
Ah,
19 is stated about matched filters. So that's the end of the matched filter part.
we yeah, that was all about match filters.
Okay.
We talked something about match filters.
Yes, sir. In the end.
Yeah, that was about it. So I said that we had discussed match filters in the previous semester. So I won't be redoing that stuff.
Yes, sir.
I'll just reintroduce. I just reintroduced another way of looking at match filters. Fine. So this
Yes, sir.
S1T, so I1T, and so on. Now, therefore, we can write SM or R equals SM plus eta. Or this is how we wrote this in vector form. Right. So now this assumes that the channel between the transmitter and receiver does not change the fine. And let us now consider a slightly more general case.
Sir, isn't it changing by adding the noise?
Uh, Adit, in 5 more minutes, give me 5 more minutes on explaining this.
Okay, sir.
or change is a, or it simply adds noise. I would say that. So now consider that say the channel introduces a multiplicative gain, that is R equals some G SM plus eta. Fine. Okay. Or rather, actually, let's consider a more general case. R equals some G of SM theta plus eta. G is a vector valued function of SM and some unknown channel parameter theta. Fine. This makes it more general. So instead of receiving the signal itself, we receive a function. So instead receiving corrupted signal, we receive corrupted function. Right?
Yes, sir.
Yes. So now eraser is active. Order this blue pen looks better. To estimate the signal m hat equals x. Right?
Yes.
Yes, sir.
But now instead of R given SM, we have we know noise. So this theta is unknown. Fine. So we can only have G of R SM give SM theta.
Sir, do we assume theta to be like constant throughout the time?
Random. Theta is random. Theta is unknown and random.
Okay.
In that case, I can write this as f of r given, right? G is a deterministic mapping.
Yes.
So given Sm and theta, I can construct. So now this. So therefore, f r given Sm equals right.
Yes, sir.
So
Sir,
theta is, wait a second, Shubhashish. Theta is an unknown random parameter. Oh, sorry. With known district. And therefore m hat equals yes, Shubhashish. Now tell me.
so like what kind of parameter is theta at exactly theta vector exactly?
I'll come to it.
Okay.
Okay. So therefore also because of this, the probability of error becomes summation m goes from 1 to capital M r given Sm dr. This I can write as complement. Sorry, complement I write like this. F theta. Sm comma theta F theta. Or rather, this should be outside. So this cancels out and dr. So dr here. Dr d theta. right? And this is nothing but integral Pm.
So it cancels out as in?
No, cancels out is the wrong word. I was just talking to myself for a second. M comma theta d theta. This equals Pe as a function of theta. Oh, sorry, P f theta and nf theta here as well. Yeah, d theta f theta. Right.
So shouldn't there be a summation over M?
So that summation over, yeah, here there should be a summation over M inside. But the point is that this is the probability of error. Fine. So you can actually eat away this step. Now it is fine.
Answer above, you said that if we know f of r given g sm theta, then we can
Yeah.
find out f of r given sm theta. So when we are
No. What I was saying was that G is a deterministic mapping. So f of r given GSM theta is equivalent to f of r given SM and theta.
Sir, but shouldn't there be some functional, some function when we are doing that conversion? Because when we are
No.
doing given g of sm and
See,
theta,
given uh, uh, so see it like this. I know that r equals g sm theta plus eta, right? This thing I know.
yes, sir.
Based on this, so if G is a deterministic relation, say G Sm theta equals Sm plus theta by 2 or theta Sm or theta inner product Sm. It can be anything. I should know all I should know is what is the relationship between the two. And then for given a theta and Sm, this will be deterministic or GSM theta will be deterministic. So I can say that given Sm and theta, there's a one-to-one mapping between GSM theta. So I simply say that given Sm and theta, I can find out the probability of or PDF of receiving a signal given Sm and theta, right?
Yes, sir. Sir, so can we say that f of y given x and f of y given x cube, uh, I mean, they are the same probability distributions?
Uh, y of x given x and x cube, there's a one-to-one mapping, yes.
Okay, sir.
Okay. Fine. So this and yeah. So now consider theta equals a and g sn theta equals fine. Simple. the simplest or one of the simplest relationships between any unknown parameter, and so A is a non-negative, or yeah, A is a non-negative real. Fine. Let fine.
Sir,
Yep.
S of t just this.
Fine.
Yeah.
I was about to change that. So now D1, or rather S1 equals EB, S2 equals minus root over EB, right? Then it is minus here. Right?
So shouldn't we multiply them with the
Y-
probabilities of S1 and S2, or are they eq probable?
Yeah, assume that these are equiprobable. P1 equals P2 equals fine. We assume that these are equiprobable.
So probability of both are 1.
What?
No, P1 equals to P2 equals to 1. Okay.
Yeah. So sorry about that, but yeah, is it fine now?
Yes, sir.
So basically, I can reduce this to R such that infinity sorry, FADA is greater than 0. Fine. Fine, I skipped a step. But you can expand these squares in the exponent and rearrange, take this to the left hand side rearrange
sir.
terms and get this.
So you have deduct E R square by n naught term, right? On both sides.
Yes, that would cancel out in division.
Yes, sir.
And so expand these squares, cancel out the identical term, subtract these, and you get this. And you can, after some jugglery, show that given now for a given value of a, right? And consequently, fine.
Yes, sir.
Yes. So if you, so if the channel introduces an arbitrary gain, the probability of error changes. Fine. So far, so good. Now let's talk about one specific case, or let's talk about a case where case where a is still a real number but no longer non-negative. What do we, so can someone, so the same case s1 equals root over eb, s2 equals minus root over eb. Can someone identify the big problem here? Or what will be the problem that we will face? I will obviously identify it, but
Sir,
I'd
it
like
can.
that.
So the channel can push the signal or the symbol to the other side.
Yes, precisely.
Yes, sir.
So
The domain problem.
the
Yes.
channel, if unfavorable, can cause error with probability 1. So in that case, the probability of error actually is probability that a is less than 0, because if a is less than 0, you will almost surely have an error, right?
Sir.
Or you have a double error, but that is quite low. That probability is quite low. So probability that a is less than 0 plus probability that a is greater than 0 I'm not considering the case where a equals 0 because that is a singleton event. So probability, and actually this should be plus integral right, this beast. So we have this beast, or we have the probability of error looking like this. Now the point is, so the channel phase is and see that the orthonormal functions. Did we call them psi or did we call them phi? The basis orthonormal functions.
Sai, sir.
Yeah, functions psi1 t. So suppose you transmit.
Sir, in the beginning of the lecture, you showed the block diagram. So they had the orthonormal functions.
Yes, so I
So
should make them
those
phi
were
as well.
So those are 5.
Yeah, so I will make them phi once. So you can replace those with phi, because generally we use both psi and phi for orthonormal functions. Both will work. Unknown. So suppose you transmit, suppose say PM at time t. Fine. So what you are doing is basically this is a transmitter, this is a receiver. Basically radiate. That's what we do. So you are transmitting, say ST equals AM cos right. This is what you are transmitting where
yes, sir.
or psi t. Fine.
So why root 2?
Uh, for unit energy.
Okay.
So now you transmit this and we receive right? This so physically, what am I missing?
Sir, A will be multiplied with the amplitude.
Oh, no, not here. If we talk about a real practical propagation channel, then assuming even assuming that the channel is unit gain, there is still that something that we are missing.
Sir, we are not
Time
considering.
shift.
Yes, time time delay. So t minus some tau, right?
Yes.
So now at this receiver, what I do is, in order to construct R, what I do is I multiply am cos 2 pi fct, or what I actually do is conjugate is not needed, but still. This
Yes, sir.
so what this will give me is actually t am cos 2 pi fc t minus tau, right? Oh, right. This thing
Yes.
plus eta t, obviously, plus eta, right? Agreed, guys?
So won't the cos 2 pi fct be multiplied with eta?
Eta t. So I've reduced that part for you.
Okay.
Eta t, that has been reduced to the noise component. So this will give me am. I'm skipping a step. Cos right.
Yes, sir.
So now I have if this tau is unknown, tau is a tau is a propagation parameter, and at suppose we are communicating at 2 gigahertz, then so let's see how this, so the received signal strength or the received signal power, I'm not talking about the power. So this tau now acts as that A that I had earlier, or random channel gain, right? So the probability of error, no matter how good is the probability of error in the start, it'll actually vary with tau like this. Agreed?
Yes, sir.
Or as tau changes, suppose, yes, thank you. Yeah. So suppose fc tau equals this. Nothing, no signal, because cos pi by 2 is 0,
Yes, sir.
or rather plus k for any integer. Fine. So, and now just to introduce you to the magnitude of the problem, let's also say that so do you guys know at what frequencies do our cell phones function?
Sir,
900
2.5
megahertz.
900 megahertz, 2 gigahertz, 2.1 gigahertz.
Yes.
So I can say that 1 gigahertz is a good enough frequency.
Yes,
Yes,
sir.
sir.
Fine. So which means that so now for a 1 gigahertz signal or 1 gigahertz signal, the timing error between transmitter and receiver that can destroy everything, approximately 1/4 nanoseconds, right? Do you agree on this?
Yes, sir.
So it's not that a smaller timing error will help you, or you can say that okay, for timing error of greater than of if the timing error is 1 nanosecond, then we are safe. It's error, and it can go haywire in any way, or it can cause problems in any way. So if you have an error that is of the order of 10 to the power minus 10 seconds, you can land in trouble. So uh, 1/4 nanosecond is 2 into 10 to the minus 10 seconds.
Yes, sir.
So now I hope you understand. So all this we leave to VLSI people, that you develop clocks that are this precise, that allow us to go to or achieve such levels of precision. Now we will do one more case where so in general for an in general for an arbitrary phase RL or R equals fine, and right? So this can make life too complicated too fast. So there are two ways of countering these phase ambiguities. So any guesses? What are those two? What can be those two ways of countering phase ambiguities?
So just like we handled phase differences in last semester, so we can use the same method,
What was those?
like phase lock loop or something similar.
So for phase locked loop was actually meant to tell you the phase difference between the signal and you had a reference over there.
So then what about pilot
What?
signals?
Okay. So pilot signals are the right way of going. So one, send a signal that contains the phase information that can be used at the receiver pilots. We'll talk more about pilots in this time's quiz or short assignment, whatever you want to call it. Right? So I'll tell you that actually. So this Saturday we'll be talking about pilots, or you guys will be telling me about pilots. Fine. And to design the constellation or design the signals in such a way that we do not have to rely on the phase information, or rather do not have to assume coherence between the transmitted carrier and the local carrier. Fine. Two ways of doing these things. So pilots I'm skipping for obvious reasons. How do we deal with pilots and all? But we will be talking about non-coherent signal reception. So,
Sir,
yep. Just a
sir.
second. Yeah, that.
So this phi that is being added as a phase, is this deterministic or is this also random?
Random.
Okay.
Because the delay is random.
So the pilot signal, whatever it is basically used to like get the distribution of this phi.
Yes. Not the distribution, the value.
But that is random, right?
So you should know it. You should estimate it. Otherwise, you are in deep soup. See,
Okay.
distribution for distribution, I can tell you safely that it will be uniform. You try to
Okay.
estimate, you try to measure this physically, and it will be uniform most probably.
So the
And
pilot signal. Okay. So continue. Continue.
yeah, so what the pilot signal does is that, okay, you have a uniform prior, and it
Okay.
helps you estimate the true value. Okay.
Okay. So the pilot signal and the this signal is sent at the same time.
Yes, so pilots are much more detailed, or pilots itself, the design and use of pilot signals is a full research topic in itself. So I won't go into that much detail, but if I tell you too much now, that would ruin the
Sir,
question.
sir, is it used to figure out the stationarity of the channel?
Figure out what?
Stationarity of the channel means
Stationary? No, 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 not stationarity.
to estimate
Channel,
coherence
we
and all that.
haven't characterized the channel as a random process
Okay.
till now. Okay. So we will characterize the channel as a random process maybe in the last lecture or last two lectures. So we
So,
aren't, yeah.
so the delay is more or less known in cities, right? Like I have read in papers, it is around 3 microseconds or something like that.
Sorry?
So like the tau is more or less experimentally found for cities, right?
Delay spread, not delay.
Yes.
Delay spread is found. I use
Okay.
parameter tau. I'm using small g here to denote an arbitrary function. Is that 9.2 into 10 to the power minus, is it at 9.2 meters per second per second?
No.
I'm using a symbol tau for delay. What you're talking about is the delay spread. Again, last lecture stuff. And
Okay.
to tell you about the delay, let's say that let me give you a let me give you the magnitude of the problem. Say I am at 100 meters from the base station. Fine.
Okay, sir.
So now the wavelength is 1 gigahertz. So 3 into 10 to the power 8 divided by 30 centimeters. Fine.
Yes, sir.
So the wavelength is 30 centimeters and the phase changes for lambda by 4. Fine. So I'm sitting here. I'm talking to someone on my phone, and I simply switch the phone from my left hand to my right hand. That that 15 centimeters. 15
Yes, sir.
centimeters is 15 centimeters is your small scale, right?
Yes, sir.
So if I switch the phone from my left hand to the right hand, is that 15 centimeters? Will that delay be known? Will that change in the delay be known?
The phase will change by then.
Yeah. Phase will change, and that destroys everything.
Okay, got it.
The phase change that is caused to the delay actually destroys everything. Note that. So you get the magnitude of the problem.
Yes, sir.
Yeah. So I would start with non-coherent detection, but apparently we are out of time, right? Yes. Yeah, we are out of time. So I'll stop here and we'll continue discussing this problem tomorrow.
Thank you, sir.
Bye.
Bye, sir.
Thank you, sir.